exactly like this. So they are a way in which you describe patterns of characters, and you are able in this way to extract from a certain string all the patterns, all the strings, the substrings that matches those patterns. And this is the module that I'm using. Luckily, it's already built into Python. This is another one related. And to understand what's going on here, let's suppose that you have this is our word, okay? And if you want to see this, the word is this long string here, okay? So when we say find all, means try to find how many occurrences of this regular expression, which is a fixed one, so exactly AWA, you can find in the word. And if you evaluate this, you see that there is one occurrence of AWA into the word. A technicality which has proven to be interesting from a theoretical point of view. Well, I'm using the dot symbol, not by chance, but because in the typical description of regular expression, the dot symbols stands for match all symbols. Then I realized that this was a good idea, but not the best idea. Why? Because at the end I decided to create my word from a subset of the ASCII encoding, and I will use only lowercase letters. Okay, so the word is made up only of lowercase letters. This is just to simplify the idea. So the point was that if I use directly the dot symbols, it means that it matches all the possible ASCII characters, and if I want to generate rather than find a possible occurrence for a type, I will have back also other characters that are not into my starting alphabet. So I defined this simple function that creates something like this. It's a conversion utility, and this conversion utility take a certain type, like this one. You see there is a dot, and at the end what happens is that the converted type looks exactly like the same. So you see A. Then we have a special strings matching all characters, and then you have again the A. So this is a sort of reduced form of the dot characters, and I'm defining a conversion because I want to deal with this. They are easier to see, and then I delegate the computer to convert these types. So this converts all the types. No, there is something. You see that the something is complaining. Because I have not created the code. Sorry. You see that it is interactive. So when I made a mistake, I am beaten by the computer. So let's see if I've been a good student. Yes. And this is my converted code. If you remember, the code is exactly the same. It does with these long strings, but actually it's the same form. So, given that, can we define what is an interpretation in this very, very limited context? And I defined an interpretation function. So what is an interpretation? Well, actually, interpretation is to find expression and to associate content. This is pretty basic and pretty general, of course. It is very simple. So the idea is that this interpretation function gets takes a word, takes a code. Then what happens is that it tries to find for each sign function in the code, tries to find all the matching into the word, and for each of the matched expression occurrence, then generate a possible content following the content type, and it returns. Then it means it gives you back interpretation as a list. So I tried to see what happens with this, and I got this interpretation that I'm showing you. This is my interpretation of the word. So you see that I spotted AWA, there is one, and then I generated BBF, Then, following the don't care symbols that are present in my expression, you see that I get Z, RZ, ZFZ, because they both matches the same expression type. And I have a content type which includes don't care symbols, so I get G, NG, G, Z, G, and so on. In other case, I have these pattern ears, and it requires to generate always this triple O content. I'm only working with triplets. Why? This is again a sort of decision to have things easier. So I will work with triplets. I will describe types in terms of triplets. So there are some interesting aspects in this model which is so abstract in relation to semiotics. Well, the presence of don't care symbols differentiate the types because a sign function, as we see, can include or not open or closed type. We can say that an open type is a type including don't care symbols, while a closed type is a type that has no don't care symbols. So we can also differentiate between a closed sign function made up of all closed type and an open sign function, in which sometimes includes don't care symbols. And so on one side we still get the same structure, but on the other side we have this code which is not deterministically related to certain specific production on both expression and content side, but it can match much more occurrences. So the replica library is still working, of course. What is an interpreter in this specific content is a set of sign functions, that is a code plus an interpretation procedure that I have defined through a function. Recognition is the main task of this interpreter, and well, it's interesting to see what happens with closed and open types, because if the type is open, then there is a variable amount of freedom expression. So we can think in terms of allography and autography in terms of Goodman, because strict allography follows the model of the replica, and in that case it means that you have to match exactly that, so closed types. On the other side, the idea of autography is not necessarily the opposite of. It's a sort of continuum axis between strict closed type and completely open type. So this idea of open types make us think about strange cases. Now, what happens with something like this? So you have this matching everything, and so everything can be matched, and the result is counter-generated like wow. So it's a sort of strange sign function like stupor mundi, you know? Everything works, everything, no? It is possible formally, and actually it matches some strange behavior. We know people, having this sort of exaltation from everything they are able to find. Now, this is fully open, but everything leads to interpretation, everything is significant. This always works, but it works poorly, of course, because you get everything. There is no difference. Difference is what creates value, we know, in structural semiotics. So, we can think of specificity following Holland, a formal characterization of this type. And how do we provide a score for this specificity? Well, it's easy. We count the number of dot symbols. So the point is that if we have no don't care symbols, it's fully specified. On the other side, if we have all dot symbols, then the specificity is 0. So we can provide, and this is interesting, we can provide a score that is what Holland calls credit assignments, which is crucial for adaptive system. In order to define an adaptive system, you have to provide credits. You have to assign credits. In genetics, fitness, it's the main credit, let's say, assigner, in the sense that if you're able to survive, then you get the right to reproduce yourself. So it's the relation with the environment that gives you back something and says that you're better fitted or less. So, suppose we have another strange cases like this. So we start with something very specific, and then we can say everything of it. Well, does this very simple model sounds interesting? Well, actually, if you think about the debate on deconstruction or on over-interpretation, the point is exactly that you start from something very specific, let's say a poem by Tennyson, and then you can speak of everything. I'm of course making a very simple description of very complex situation. I'm making a parody of this, no? But actually the point is that the whole debate starts from the fact that, yes, you look at Raphael and you speak about word second. What's the point? Okay? So again, this model is possible, but we know that it works poorly again. So we can provide a sort of general credits in which we calculate the specificity of a sign function by these times using a multiplication between the specificity of the expression and the specificity of the content. Why using the product? Well, it is interesting, the product, again, comes from Holland, because it means that if you are fully open on one side, you always get 0 as a result of your interpretation score. So I'm working on interpretation score without knowing nothing of my model. I just work with letters, characters, but I'm providing an interpretation score. So of course we can have this bizarre aspect, no? And you match everything, you can say everything of it. So this is sort of anything goes sign function. If we give this definition of interpretation score, it means that all types having a completely open type, all sign function having one completely open type, they get zero interpretation score. Now, can we calculate this? And so I say, okay, that's easy, because we can calculate the specificity by taking the number of the dimension of the string of the type, let's say 3, and then we simply remove the number of occurrences of the don't care symbols. And as an example, you calculate the specificity of this, and you get 0. And of course, now we have to redefine the convert types, because in this case, what happened is that our new converted code, it has both the expression types, the content types, and generic scores given by the product of the expression and the content type. So we have sort of an idea of strength in terms of interpretation score of each sign function. Then we can redefine our interpretation in this way. We can calculate a global interpretation score, because we apply to the word all the sign function. We get a score for each sign function, and then we sum everything. And we see this code, given this word, what does it get back? And as an example, you have that this interpretation here of our word gives you back 156 as a global score. What this quantity means? It means nothing, but it means it gives you a possible idea to compare with other interpretation. So what happens here is that I'm working with an abstract model of interpretation, but I have not taken into account other aspects. I will try to go fast on this. So I'm working on recognition as a generic framework. So the idea is that it is a meta label, but I'm speaking about replicas, because the code at the end, even if it weakens, the model of replica still works with replica. What happens with ostension and invention? Now actually, Eco says that ostension occurs when a given object is picked up by someone and shown as the expression of the class of which it is the member. You lost a screw or something, you go to the shop with another screw and say, I need 3 or 1 of these. So you're using this object as the expression of the class that it represents. So Eco says this is the case in which we have the point that the possible method of the expression is the same method of the possible referent, because it's the same stuff, semiotically. And can we provide a characterization of this idea of homomateriality in such a reduced framework like this one. So I started thinking and said, okay, we can say that if we have the same characters in the same position, then we have a possible idea of homomateriality. The point in homomateriality is that, and in Énonciation is that something is sort of part of the content, there's this inclusion, metonymical relation with the content. So I'm using as a possible way to describe Énonciation to have the same characters in the same position. Only the same character is not enough because we're working with an alphabet, it's a small one, so of course we will have something like this. But the point is that it's just like a part, sort of locus genetically. A part is included in the same position in expression and content. So this is my definition of ostension. Well, we could calculate a degree of ostension at this point. And we know that this degree can vary in possible examples. If I see a scarf in a shop, I go buy the scarf, then actually they give me a scarf exactly like the one shown in the shop. But if I see a tissue, they make me see 1 square meter of tissue, then they give me a piece of this tissue. So, different operation. More interesting, can we give a notation for ostension? Well, I came up proposing this, where the capital O stands for special characters. This is a standard, don't care if we want symbols. And this couple of underscore characters represent special notations, meaning that we have to copy these and these in the same position. So we have a notation for possible ostensions. And of course this means that this is a sort of rule allowing us to extract content from expression, and we have to how can I say, deploy one from the other. So we have to convert these so that we get to these at the end. Special notation differentiate the two. Okay, we can do that. I'm skipping this. Now, what happens with invention? The idea in invention is that actually there is a rule connecting expression and content. And the point is that the manipulation of expression says something about the content. So if we see a letter and we see it bigger, well, if it is an A, it remains an A in writing. But if you see an imprint and you see it bigger, it means that the animal is bigger. So there is a relation between expression and content. And there is a causal link in some sense that requires us to go from the expression to the content. Can we describe this idea of a projection rule between expression and content? Well, this is a bit difficult in terms of notation because it means that any kind of mapping procedures can be used to describe the relation between the expression and the content. I am here proposing a formalism like this. This is really related to Python in the sense that this is a very compact form of notation which is called list comprehension. So the idea is that we can describe imprint in terms of a special characters like the O of extension, here it's imprint, plus a description in mapping expression to content. This gets complicated, it works, but of course ostension is more general, imprint is a bit more complicated. But what is the point here? Is that at the end, in order to work with our model, we still have to take this code, eventually including ostension and imprints, and convert it, expand it, so that we get from, let's say, from AB, this is a code shifting each character to the next character. So if we have AB dot, we will get BC dot. At the end, in order to work with this model that I have put up, we still need to expand this ostension and imprint and to have final model, which is our standard model. I will call this operation which is originally it is an implementation procedure, I would call this a sort of replica reduction, because at the end I'm still converting all these ostension imprints into replica. So it's replica reduction. Is it interesting, this replica reduction? Isn't this a form of reductionism in relation to echo? Maybe it is, but on one side it includes the possibility of describing signs in terms of also ostension and invention or imprint as you want, and replica. On the other side, the notion of replica has been so successful in semiotics because it takes into account these very basic aspects of sign, which is that aliquid stat pro aliquo, something standing for something else. So now I'm working with replicas. And what happens here is that I'm doing this very fast. The point of making interpretation and to calculate score is not totally accidental, but the point is, can we have a sort of adaptive system working with this model of interpretation? So the point here is that I'm defining some rules to create random calls and so on, but my main idea is, let's suppose that we have an agent, let's call him an interpreter, working with an environment, and this interpreter is provided with random rules. It's just plunged into the environment, probably like first protobacteria. And suppose it has some rules working in this. Is there a way to make this interpreter learn something more? And of course, this is inspired from genetic algorithms. The idea is this one. If we have a credit assignment system, like the one I showed, because I'm providing a score for each interpretation, no? So there are sign functions that matches and they get more score. Some sign functions, you cannot find any expression occurrence, so they get a 0 score. So the idea is that you start with just four sign function. You try to match the word, and you look at the score. If you find something that has matched, then you rank this sign function. Suppose we have 4. You take the three having the best score, and the lowest score, you throw it away, and you replace in the next iteration with another random score. So what happens in this case? Does it work in some sense or not? So here you can see, I hope the code works because I have to evaluate everything. So this is an algorithm used to rank sign functions. And this is a function making the top code, so selecting the first 3 in this case. And this is the interpret and update functions. It means that it takes an interpretation, it looks at the score, then change the code in an opportune way. And finally, this is my small function to provide an iterated interpretation. So what happens in this case? Just out of curiosity. So we make a random code. Let's look at this. This is a random code, right? I am generating it randomly. Then I'm converting it. Then I am running this algorithm for 200 times. So what happens is that I am matching the word with those code. Then look at what happens. Is there something good in it? Keep it. Remove the worst sign function, then get another one. So what happens in this case is that we have 200 iterations, and if you start from the beginning, you see that by doing random things, you don't get much because you get 0 score. So actually, these are your sign function provided with a structural score, but they match nothing, so it's 0. Then you start and you always get 0. You get 0, okay? Right. Then you get something, 9. Evidently, let's see, here something has matched. RXH, which has been introduced later by the way, matches. So it gets on top position. Then let's see if we get better and better. You see that we keep this rule. Actually we have 27, it means that we get something more. And by the way, here don't care symbols are very important because they have, of course they have a smaller score, but they match more actually, because they can match more possibilities. So the interesting point here is simply that a system like this that has no idea of what is in the world, at the end it keeps on improving its performances. So at the end, after 200 iterations, you see that you have 66, 54, because what happens in the dynamics is that, which is typical by the way of this system, is that at the end you have 78. What happens is that you have 0, then you have a sort of linear growing, then you have a sort of plateau, and you oscillate around the plateau, then you have a small increase typically, and again you oscillate in this plateau. We're only using 4 rules and we're getting this score of 78. So that was interesting because a random system like this is able to learn something because it keeps the good sine functions and it improves its possibilities. So the systems look adaptive. It has strange behaviors. Now you will say, okay, but what about content? Because this is just pattern matching, right? So there's no idea of content. Of course, content is a complicated issue, and I made some experiments that I will show you, try to show them very fast. So maybe the whole system can be retranslated in genetic algorithms. Maybe. I think it is interesting because it still deals with a notion we are used to in semiotics and to which in some sense we are there. It is a sort of bare-bone mechanism. It only works with formal properties of the system. I think it is interesting to consider this notion of replica and this notion of code and to expand it and weaken it by means of Docker symbols. Of course, the main point here is that we have done nothing with the content. Actually, we get a characterization of this small interpreter. It's an interpreter provided with a small memory. It has only 4 sine functions, and each way it delete a sine function and have a new one. Is this a working possibility? Well, we know that our memory keeps on expanding, but ecologically we also know that it cannot keep on expanding at infinite. So we know that small agents in nature, they have small memories and they have to deal with a variable environment. So this is a strong limit, which is interesting, but and it's a sort of ecological limit. So, what to do with content? Now, actually, if we consider what happens with John Holland, we know that ecologically, the main idea, if you want behavioristically, the point is that you do something. If you spot something, you do something. What can we do in our string world? Well, actually, the point is that we have a type for content. We can generate occurrences for this type. And what to do with them? Well, we can store them if we want. So, like our agent keeps all this information. Totally useless. It's a bit strange. Also because it reintroduces a sort of dualism. Because we have this interpreter working on the world and keeping where we don't know exactly, maybe in a memory, all this content. But the point is that each semiotic action should be, for someone like Peirce or Eco, that are more interested into these aspects, it's an action on the world. And a very famous discussion by Eco concerns the epistemological status of the disciplines, and he says, okay, you have to think about semiotics not in terms of an exploration of the sea in which the trail of the ship gets lost, but like moving, in English is into a forest, and when you move in the forest you have to cut down some trees, some branches, and you explore in the forest. The point is that you are modifying the forest. By the way, this idea of an ecological imprint has been shown as very important in the transformation of the environment, not only by humans but also by various kind of animals like elephants. Elephants, they transform in a radical way the environment thanks to their dimension. So my idea is that you have to do something with this content, and of course I have no other determination, only string.